We're back from the break. This should be Chem27ABlake. For chapter 8, we did a bunch of questions up to everything up. We did Lewis structures, which is a big thing. We started really chapter 8 with Lewis structures. We did some stuff with covalent compounds, and we did everything up to molecular geometries. And we took a test over that part. We're going to pick up with the remainder of chapter 8 with molecular geometries now, which is about the shapes of molecules. Remember, molecules are covalently bonded. You're taking two nonmetals from the upper right-hand side of the periodic table and sharing electrons to covalently bond, and that makes molecules. And those molecules have shapes, or molecular geometries, based around a central atom. Okay, so once we do Lewis structure, and you've got some molecule drawn on paper with sticks, you have to apply valence shell electron pair repulsion theory. And all that's saying is the electrons are going to push atoms around and lone pairs of electrons in a molecule to change its shape so the electrons can get away from each other. We talked about this some already. Now, on page 261, at the bottom of that page, there's a drawing of these three shapes. We have linear, triangular, planar, and tetrahedral. And these are a result of hybridization, which often students are like, can you explain hybridization again? Well, hang on, got to get my sound up. I have a sound reflector that I put up here, and hopefully that gives you a little better sound. You may have that problem with hybridization, you're not real sure. Just go with it, I think makes it a little bit easier. It is what it is. Not all that much to understand, really. But at the bottom of that page, they show the result of a hybridization, and you could have two orbitals. In this case, they'll be sp orbitals. In this case, it'll be something in the alkaline earth metals, beryllium, magnesium, or calcium, or strontium. That's a central atom. And there's making a bond on one side and a bond on the other side. Now, by the way, that does not follow the octet rule. The octet rule is followed by the ones on the right side, but as you go to the left, some end up with 6 pairs, or 6 electrons, some end up with 4 electrons, and these guys end up with 4, 2 here and 2 here. Where that comes into play here is we're trying to talk about valence shell electron pair repulsion theory. So if all you have is a shared pair and another shared pair, they will try to get away from each other by 180 degrees. See, valence shell electron pair repulsion theory explains this shape. So does hybridization. Both explain it, but in a different way. If you have 3 pairs of electrons, according to that figure in the book, that figure's a little bit better, they do it with balloons, they are in a plane. I'm not sure what's going on here. I know why I did that, but I don't want it on this page. And that plane here is this time, and I've got one that way, one that way, and one this way. If you think about it, these are 120 degrees apart. They're 180 degrees apart this way. If you try to go and bring one up, that angle gets less than 120, which can't happen. The way they can get farthest away from one another as possible is to be 120 degrees apart. Now, if you're explaining this same thing, instead of with valence shell electron pair repulsion, with hybridization, the kind of hybridization you're going to see here is sp2. We're going to talk about that. Tetrahedral is you've got 4, so you got kind of 3 down and 1 up. Take a look at the balloon in there, the balloon picture in the book. Those angles are about 109.5 degrees between each one of those, and they're split evenly no matter how you do it. I guess I could pull the models out and show you these. Let me see if I have one quick. I guess I could try it. We're not really set up for this. Tetrahedrals like so. Every angle is 109.5 degrees, no matter which way you do it. And it's radially symmetrical about the central atom. 109.5. To get as far away from each other as possible, they have to be that way. Triangular planar. Let's see if I can pull that one off with my models here. Give me a minute. It's not that one. It's not this one. It's not this one. Which one do I not look at? Here's a triangular planar. If I did this. Here's one. This is a triangular planar. Like so. In a plane that makes a triangle. And this is just a straight line, linear. I'm not going to look for that one because I'll probably have trouble finding the molecule. Well, I could do it this way, I guess. I can do it this way. This one doesn't get used very much. This would be linear, like so, in a line. Okay, going on. If we explain the same thing by hybridization, which is figure 19, page 262, which I need to pull this out of the book, maybe, and include it, but it's this one, right here. There's another way to explain this. Along this side, I don't have it labeled, but this would be energy. And what nature likes to do is go to the lowest energy level. That's why you like to lay in bed in the morning. Or, you know, you prefer to bring a pillow to class and put your head on the table and relax. That's what nature wants to do. That's from an energy conservation standpoint, that's what people want to do. To an extent. We want to do the things the easiest way. And if you are looking at energy levels up here, this is higher. So to have p orbitals, which are higher energy than s orbitals, with 2 electrons here and 2 down here, that is more energy overall than having shared orbitals. I guess I used the wrong word there, shared, but to have hybrid orbitals. So how a hybridization model explains this is you take an s orbital and 3 p orbitals, that one, and that one, and you combine those 4 orbitals to make a new kind of an orbital, an sp3 orbital. And there's 1, 2, 3, 4 of them that each have 1 electron, which works well with Hund's rule. Every orbital gets 1 electron before any gets 2. So you don't really want 2 electrons here with a vacant orbital there. It's not as energetically favorable. It's more favorable to hybridize those and have one electron apiece. Now this is just a way to explain it, what's going on. And when you do that, you end up with this, in theory, this shape here. This tetrahedral shape, sp3. Okay? If you do sp2 hybridization, you're going to hybridize one s orbital with two p orbitals. And when you do, you have 1, 2, 3 electrons in 3 equally identical orbitals. And those come out to be this guy. Triangular planar. I don't understand. Well, just go with it. It's a little bit easier to just go with it. sp hybridization explains if you take, oh, by the way, you have 3 electrons here, and it's best to put them in 3 equal orbitals rather than have that one empty, and certainly to have that one empty too, but nothing you could be done about that one. If you do sp hybridization, you're going to take an s orbital and one of the p orbitals, and at least you'll have 2 orbitals with an electron in it. And when you're done, you end up with this guy, the linear. So the alkaline earth metals do this. The boron family next over does sp2 hybridization. The next family over, carbon family, does sp3 hybridization. Those 3 families do hybridization routinely. Is that the only hybridization there is? Well, no. But that's all we're going to talk about right now, I think. Okay, which leads to molecular geometries. Here I went and grabbed a black atom out of my molecule kit, because that's carbon. In fact, I happen to have 4 hydrogen stuck on there. It's just happened to get methane. Now where I'm at this point is on page 263 with molecular geometry. So I'm going to talk about all of these, but not from the top going down. It makes more sense to go here, here, and then I think here, and then there. Jump around in there. Starting with the simplest one is really CH4 tetrahedral. There is a section about polarity in here. Where's this at? I don't know where I got to it. Did I start with it? Did it not get saved? I remember taking a picture. Okay. Here it is. Electronegativity and polarity. Let me jump ahead a little bit. Maybe I need to move this. This is what, page 43? This is probably something we've already looked at. Well, I'm sure we've already looked at because we talked about polar bonds. But now, this matters molecule-wide. So if I take any 2 atoms from the periodic table, there's a periodic table of electronegativity. I don't remember what page it's on, but I'm pretty sure we looked at this. And when you subtract them, you decide whether or not the molecule is polar or nonpolar. Or at least if that bond is polar or nonpolar. What we're going to decide now that's different is we're going to take the molecular geometry that's with it and decide if the molecule as a whole is polar or nonpolar based on all the different charges adding up. All the different polarities adding up. Okay. So if I look at carbon and hydrogen in that periodic table of electronegativities, carbon is 2.5, hydrogen is 2.1, subtract that and get 0.4. According to that table I just showed you, that's right on the bubble. 0.4 has some dipole this way, some this way, some this way, some this way for each bond. And each of those bonds are identical. So if that molecule, this one, methane, has 4 bonds, and they're all polar, they all have a dipole towards the center, the molecule is nonpolar. Why? How can you have 4 polar bonds make a nonpolar molecule? Because they all cancel out. They're all pointing towards the center, and they all will cancel one another out. The molecular geometry there is tetrahedral from that page. And the molecule is nonpolar. Now, if you don't get that, ask about it when you're in class. Let's go to the next one I'm going to do off there. I'm going to jump up one, down one, and go to ammonia. That molecular geometry is triangular pyramidal. Your book calls it trigonal pyramidal. And I've got an ammonia, or a nitrogen atom right here. I'm going to stick some hydrogen on it. And here we go. What you've got is a little pyramid made with 3 sides. Okay, that's called trigonal pyramidal by this book. And then out the top, you have a lone pair that's not there. This one doesn't show it. There's a lone pair up here that pushes those other ones down. That's your valence shell electron pair repulsion. Got a pair of electrons up here pushing those electrons and these bonds downward. And this is the shape you end up with. Now, if you take that table and look up the periodic table of electron negativities, nitrogen's electron negativity is 3. Hydrogen is 2.1 apiece. So that bond's polar, that bond's polar, that bond's polar. Is the molecule polar? Yes. Because these aren't exactly in across from one another like they are here in this planar one. They're at an angle. And those 3 angles add together to give you an overall polarity this way. So your molecule ends up with a positive side and a negative side. This is delta, Greek letter delta. It's positive and negative. By the way, you can find your Greek letters probably in Schoology. And if you forget that, or you want to look this up, or you want to look another one up, virtual handouts. General course reference, probably Greek alphabet, in case you run into that. Okay, let me see how we are on time. Okay, we'll stop with that one and continue. Probably, I would imagine we went from methane methane to ammonia. We'll probably do water next before I jump up there to those other ones. Water gonna be next? Yep, water's next.